Hello and welcome to this talk about our paper called Fractional Covers of Hypergraphs with Bounded Multi-Intersection. My name is Matthias Lanzinger and this is joint work with my colleagues Gottlob, Reinhard Bichler and Igor Raskom. We'll introduce the problem, the setting in a more exhaustive fashion. We'll introduce this bounded multi-intersection property that is mentioned in the title, which we believe has a lot of potential in many directions of hypergraph study. And then finally, we'll introduce our main result, give a brief proof sketch for this main result. The actual proof is very technical and I refer you to the paper for details. And following that, we'll briefly look at two applications or corollaries of this main result. And that's it then. So yeah, we will start with fractional edge covers and their support and what these things are. So this whole paper will be talking, this whole talk will be about hypergraphs. To briefly recall this fundamental concept, so hypergraph is just a tuple, consists of a set of vertices, which is just a set of any kind of elements, and a set of hyperedges, which is a hyperedge is just some set of vertices. So you can also, hypergraphs are also commonly viewed as just sets of sets. Right, and for the sake of simplicity, we assume that these hypergraphs are always connected in this talk. This makes no real difference for the results, but it's just easier to imagine. So this is a good way to move on to what we are interested in as our principles of object of study, which are edge covers, and particularly fractional edge covers. So we start with these edge weight functions, which are simply functions that map a set of edges, or the set of edges, to weight between 0 and 1. And then we have vertices that we call covered by such an edge weight function, which is defined here as this B of gamma. And this simply contains the vertices where the incident edges, if you take their weights, these weights sum up to 1 or higher. Right, and in particular, if all the vertices of a hypergraph are covered by such an edge weight function, then we call this a fractional edge cover of the hypergraph. And if we restrict the weights to just 0 and 1 without the whole interval in between, then this is called an integral edge cover. You may also know this problem as the set cover problem, which is the exact same thing as what we call the integral edge cover problem here. But we're mostly interested in the fractional edge cover problem because this presents new challenges, especially when it comes to support, which we'll introduce soon. So just a brief example, with this triangle graph, vertices ABC and edges between each of them. If these two green edges here are given weight 1, we see that all the vertices are covered, and therefore this is an integral edge cover. You see even A has total weight 2 incident to it, but this is fine and allowed. And alternatively, if we want to use the power of the fractionalness, we can assign 1/2 or 0.5 weight to all of the edges. And it's easy to check that then again this sums up to weight 1 for each of the vertices. Thus, this is a fractional edge cover. So, but I think these concepts are probably familiar enough to most. So then we move on. So the main aspect of covers that one is usually interested in is the weight of the cover, which is simply the sum over all the weights of the edges. So in our previous example, we had the integral edge cover of the triangle had weight 2, and this fractional edge cover had weight 1.5. And in particular, there's always a minimal weight edge cover of a hypergraph, and we will call this the optimal edge cover here. So now we finally come to this idea of support. which is not, I think this is a much rarer or much more exotic, maybe until now, aspect of covers that is usually not, that is not studied very much. So the support is simply the set of all edges that have non-zero weight. So all edges that contribute to the covering in some way. If we look back at basic examples again, in the integral case that we had, only the edges AB and AC are in the support, while the edge BC is not, because it's assigned no weight or weight 0 in our setting. And alternatively, in the fractional case we had, we have all the edges in the support. And this already sort of foreshadows the problem that we're interested in, that the fractional weight can be lower, but this comes at a trade-off that more edges become involved. So the support grows and can become larger in the, or very large in the fractional case. So to make this maybe clearer, we have this example here, where I have this hypergraph with vertices. As vertices, we have the integers from 0 to n. We have one very big edge that covers all the numbers 1, 2, 3, 4, up to n, every number except 0. And then we have edges from 0 to every other number. So for integral edge covers, we see that the problem is quite boring. We still have a cover with weight 2. And in an integral edge cover, of course, the support is the same as the weight of the cover, because if it's not 0, then the weight is always 1. But in a fractional setting, things become a bit more interesting now. We see the optimal cover of such a graph assigns weight 1 over n to all these edges from 0 to another integer that are marked in orange here. So then we see 0 is covered because it has n edges, each with 1 over n weight incident to it. And the big edge at the bottom that covers everything except 0 is given weight 1 minus 1 over n. And so we see the total is 2 minus 1 over n, thus lower than the integral cover that we had before. But the support now grows with the size of the hypergraph. Right? It always, to achieve this optimal cover, you need to use all the edges of the hypergraph, so n plus 1. So hopefully this gives a bit of an intuition about why the support becomes an interesting object of study when we move to fractional edge covers, because once we want to enumerate maybe the sets of vertices that are coverable with low weight or something like that, it becomes interesting to bound the support if we want to have time bounds or size bounds on or combinatorial bounds just on how many combinations there are of coverings for specific vertices or things like this. So the question that for us resulted from looking at these things is, suppose we have a set of vertices V prime, and this V prime can be covered with weight at most k. So can we also cover this V prime keeping to the same weight bound, but now also having the support bounded by some function of the weight? I mean, the example before just showed us we can't do this for optimal covers, right? Because optimal covers can have unbounded support. So we have this upper bound on the weight instead. And so this question is not completely out of thin air. There are previous results that already give us some information on this. So the first theorem is if we consider the degree of the hypergraph D, then actually we can even make a statement on optimal edge covers. So if you have an optimal fractional edge cover gamma for hypergraph H, then the support of gamma is always at most the degree times the weight of this cover. This was stated actually quite a while back, essentially by Ferredi in 1988. It was stated on actually for Vertex covers on graphs and instead of degree for rank, but Vertex cover is at the edge cover on the dual hypergraph, and rank in the dual becomes the degree. So this is basically the same result that Ferredi had back then. And more recently, we looked at hypergraphs where the intersection between any two edges is small. So we have this property here that the cardinality of any two edges is at most I. The cardinality of the intersection of any two edges, of course, is at most I. And then if there's a gamma, an edge weight function gamma with weight at most k, then there also exists a different, possibly different edge weight function nu that is also weight at most k, that covers all the vertices that gamma covers, and that has boundable support, so boundable by the weight and by this parameter I that we call the intersection width. So this was already quite surprising because now this means we can, in polynomial time, if we consider the I constant, we can in polynomial time enumerate all the maximal subsets or the maximal sets that are coverable by some constant weight k. If we can bound this cardinality of the intersection. So, and this brings us to what we do in this work. So we want to move on to multi-intersection, which is a vastly more general property than this intersection width, as we will see soon, very soon. So we have this concept of CD hypergraphs. So a hypergraph is called a CD hypergraph if the intersection of any C distinct edges is at most D elements. So this is a very sort of direct generalization of this intersection width idea, but instead of two edges, we also make the number of edges whose intersection we care about is also a parameter now. And so, alternatively, if we consider a class of hypergraphs and C and D are constant, such that every hypergraph in the class is a CD hypergraph, then we say this class has bounded multi-intersection, which I think is an intuitive enough name. But this is not just a straightforward generalization of intersection width, but it's actually it turned out that this is a very general and very interesting property in a sense, because it generalizes many important properties that have been used until now. So bounded rank is a very common property studied in hypergraphs. It's not defined here, but rank is the size of the largest edge. So if every edge has at most cardinality R in a hypergraph, then it is a 1R hypergraph. So bounded rank is a special case of bounded multi-intersection. For intersection width, the case is very simple, as we simply generalize the number 2 to the C in this CD hypergraph notion. So any class with bounded intersection width also has bounded multi-intersection width. And maybe more interestingly, also if we have degree at most D in a hypergraph, this is a D+1 zero hypergraph, right? Because the intersection of any D+1 edges has to be empty, otherwise there would be a vertex with degree D+1. And so this is quite interesting because now multi-intersection generalizes this one thread of rank and intersection width, and also generalizes bounded degree, which is a completely different property in many ways, and it's not connected to rank at all, except over the dual. But there's no sort of direct connection between rank and degree. But multi-intersection generalizes both of them. And finally, also bounded multi-intersection is equivalent to forbidding large biclicks in the incident graph of the hypergraph. This property of not allowing large biclicks has some algorithmic use in parameterized complexity. So this bounded multi-intersection property, I hope it's clear that this is a very general property and a very sort of wide-reaching property. And so, as the title states, our goal is to bound the support of fractional covers under the 4 CD hypergraphs, so depending also on the CND. And main result that we derive for this is that there exists a function f depending on CD and k, which will be the weight, such that the following holds. So if we have a hypergraph, if we have a CD hypergraph in particular, and we again have some edge weight function gamma with weight at most k, then there also exists an edge weight function nu that again also has at most weight k, covers at least the same vertices as gamma, and this nu has bounded support, so bounded by this function of CD and k. Or we can cover any set of vertices in a fractional edge cover also in a way that has bounded support. It's maybe the sort of intuitive rough version of this. So the proof of this is very technical and has many very distinct steps. So we'll only present a sketch here of the main idea. So for the base case, so we have a base situation where the cardinality of the vertices that are covered can be considered bounded by some function of CD and k. And in this case, we're almost done. This can still have an unbounded number of edges in the support, in theory, but we can construct an equivalent cover that has a bounded number of edges. So what we do is we just construct equivalence classes that have the same intersection with this set B gamma. And then for each equivalence class, we combine the weights of the edges in this equivalence class and put it onto a single representative of this class. And then this, of course, gives us the same covered vertices, but now the same bound on the cardinality also applies to the vertices, to the support of this new construction. So this base case is not so complicated. The problem starts when we cannot bound the size of the covered vertices, which is in general to be expected. So then what we do is we split the representation in a sense. We no longer look at only vertices that are covered, but we split the representation of this B gamma in 2 parts. Part of it we look at as vertices. And this is the second component of this tuple, this pair, the U. And the other part we consider as edges. And so the edges that will cover, so we have this set S that consists of sets of edges, and particularly of at most C edges, whose total weight is at least 1. So each of these Si basically covers some part of the B gamma. And then we have this set U, which are all the vertices that are not covered by these sets Si. And we want this U to be of some bounded cardinality. So we have a bounded number of vertices plus some uncontrolled number of edges that make up the rest of the B gamma. So then we can start. We can always construct some initial pair like this from gamma by basically just taking all the edges with high weight. Those become edges in S, and the rest of the vertices just end up in this U0, and it is possible to bound the cardinality of this by some combinatorial arguments. So, but then from there on, what we do is we transform this initial pair. We basically produce a sequence of transformations on this initial pair. And there are two kinds of transformation. One we call a folding, where we remove a set with exactly C edges, and such a set as I of edges, and we instead add it to the U. So we add this intersection over these edges to the U. And because we are in a CD hypergraph, this intersection has at most cardinality D. So we can still control the size of the U, or we still have a bound on the size of the U. And the other transformation is a bit more complex. I will only very roughly explain it. We call it an extension. Essentially, we increase the size of some set in S with the intention to enable us to do a folding later on. Because we can only do a folding if it has exactly C edges. So we need to sometimes add edges first, so we can later fold them back to the U. Right, but still we can still control the bound on the U via this extension transformation. And then the sort of final step that we do is that we show that we can bound the length of such a sequence, starting at the initial pair, ending at a pair where this first component is the empty set. This then leaves us only with this set U of vertices, for which we have a bound now, right? Because we have a bounded number of steps, and in each step we can bound the size increase in the step. And then we are basically back at the base case where we have a set of vertices that we can bound in terms of CD and K. We can do the same procedure on these equivalence classes that we did at the beginning. Right, so that's the basic proof sketch. So just briefly, we'll add some applications, why we looked into this, basically. So the main reason how we arrived at this problem is the study of fractional Hypertree width, which is until now the most general width notion that allows to define tractable fragments for constraint satisfaction problems or conjunctive queries or homomorphism checking. Since quite recently it's known that it's NP hard to check if fractional Hypertree width hypergraph is at most K, even if K is constant and even if K is 2. So there's been some recent work on finding tractable fragments for checking fractional Hypertree width. Since the checking also produces witnesses, and the witnesses are necessary for the tractable evaluation of constraint satisfaction problems or conjunctive queries. And so using our main result from before, we can state the following. So if CD and K are constants, then there is a polynomial time algorithm for testing whether the fractional Hypertree width of a CD hypergraph is at most K. Alternatively, we can state that the fractional Hypertree width checking problem for some constant K is tractable for hypergraph classes of bounded multi-intersection. So, and finally, there's also an interesting relationship to vertex covers, or to fractional vertex covers. So we have this simple lemma here, where we have if H is a CD hypergraph, and then the dual hypergraph is a D+1 C hypergraph. This is not so difficult to see if you look at the sort of implication of what a CD hypergraph means in the incidence graph, and then you remember that the dual hypergraph has the same incidence graph as H. But the important part of this is that the edge cover in the dual hypergraph is the same as the vertex cover in the original hypergraph. So we can derive the exact same statement as our main result also for vertex covers. That means that if we have a vertex cover, then there's also a vertex cover where we can bound the number of vertices that have non-zero weight. So that's it. So thank you very much for your attention. The paper is of course available, in open access. So if you are interested in some parts of this, then I would recommend to check out the details in the paper. Also, there's a contact information in there if you have any questions. And so finally, I just want to quickly put up the few references that we had. And thank you very much, and bye.